Anyone, please. Good afternoon. Is my slide visible for today's
Yes,
date? Okay,
yes,
so I
sir.
will just start
Yes,
in
sir.
2-3 minutes and let people join. Okay, so in our last lecture, we finished the frequency modulation, which is a part of the angle modulation. And before that, we understood the linear modulation or the angle modulation. So before moving further, for the phase modulation, which is an extension of the frequency modulation, let's talk about ASK and FSK, which is an extension of amplitude modulation and the frequency modulation. But in this case, it is your input is a input signal is a digital signal, rather than the input signal is a analog signal like VMT is equal to VM cos omega MT, which was a analog signal. So here, the input is a digital data, which is typically represented in terms of binary digits, that is 0 and 1. So to understand this, let's understood ASK first. So basically, these are used to represent input digital data. And digital data we all understand nowadays. It is basically a binary data, like in the form of 0 and 1, or sometimes we call off and on, but it is more commonly known as 0 and 1 here. So what is ASK? So let's understand ASK. So it is basically, we say it is a form of digital modulation technique. Why digital modulation? Because here my input data is in digital form, as we'll see later on. Okay. So it is in which the amplitude of the carrier signal. Now, please note that carrier signal here is analog here, but your input signal is digital data, is varied to represent input digital data. So your input is digital, your carrier signal is analog. That's an important thing. And here, obviously, because amplitude is varied, so your both frequency and phase of your carrier signal remains same, while amplitude changes. Okay, we'll understand this in accordance with the digital data. Levels of digital data. There are two levels, as I said, 0 and 1. So if I want to express mathematically, your ASMS signal can be expressed as let me write down here and then explain to you as VASK T. What is this ASK? ASK is called the amplitude shift keying. We normally key the data either 0 and 1. So that's why the word keying has come. That means you are keying the data. You are putting up the data, either it is 0 or it is binary 1. And because in this case your amplitude is changing with respect to the digital signal, so mathematically it is represented as something which I'm going to write here. VC cos 2 pi FC T or 0. This is for binary 1 and for binary 0. So two digits are there, binary digits, which you call bits 1 and 0, binary digits. So whenever we have 1, we'll have the carrier. So this is nothing, as we have seen, it is nothing, it is your carrier signal, VCT. This total signal is VCT. Otherwise, it will be this one. Okay. The modulated carrier is, so basically, because of this expression, I can say your modulated ASK. Now, because this signal becomes a modulated ASK signal is either carrier signal, and carrier signal will be only one for binary digit 1, or no carrier signal for binary 0. And because it is this thing, ASK is also called on-off keying. On-off keying. So, but it is more commonly known as ASK, but it is a simple term that it is on-off keying. So basically, graphically, if I see, suppose I have this data in the form of binary digits. So let's say I have got this data, which is of this form. Okay. I put it like this. Then let's say this is the 1, and let's say it is 1, 1 here, again here, again here, again here. So here it is 1, 0, 1, 1, 0, 1, 0. So we can represent our data in this form. Let's say 1, 0, 1, 1, 0, 1. So this is my input binary waveform, or binary signal, or binary digital data. And let's say my carrier I represent by some other color. This is my carrier frequency. So carrier is a high frequency signal. So let's talk about the carrier. I put it in yellow color, let's say. So this is my carrier signal, which is a high frequency signal. So basically only difference is here I am getting my data is in a digital form. So this becomes my carrier signal, which is of the form of what we have called is VC cos 2 pi FCT. Okay. So my ASK signal waveform, how it will look. So I put it ASK waveform. ASK waveform, if you see the mathematical expression, so wherever there is a 1, you will get the carrier, the same carrier, and wherever there is a 0, you will not get any carrier. Okay, which I put it in the words form also in the first statement here. Okay, so here the 1 is here, so I will have a carrier here, and here there is no carrier. Again, here I will be having a carrier, and it will be having a carrier. Again, no carrier here. Again, carrier here. So that means in this case, it is no carrier. And also here it is no carrier. And again, wherever the 1 is there, so this becomes my carrier waveform. So basically, you can say it is an extension of the AM, but in the AM, my input signal is also a sinusoidal signal. Okay, but here, or an analog signal, here my input signal is a digital signal. Because it is an action, as I said, this here we are more talking about the analog communication. So these things we will learn more in the digital communication. So basically, the digital communication technique, but because it is also an extension of the amplitude modulation, we also sometimes give a brief overview of ASK also. Similarly, there is another one which is what we call the FSK. So this FSK is the experiment which we'll be doing tomorrow. So FSK is nothing, as the name suggests, it is basically the frequency shift keying. So basically, let me understand. So it is a frequency shift keying. So again, if I go by the same definition as ASK, I could define as it is a digital modulation technique again. That means just like your ASK, But here, my frequency of analog carrier signal is varied to represent the input digital data. Previously, we have the amplitude was there, either it is there or not there. But now here again I have the input digital data, but here my frequency of analog carrier signal is varied to represent the input data. So obviously it has constant amplitude and phase, but the frequency is changed. So while frequency changes in accordance with the digital data. So this is the experiment tomorrow you'll be doing. That means you will be giving an input signal, which could be 10, 10, 10, 10, 11, 10. So it is in the form of a digital data. And then you apply a carrier high frequency signal, which is a simple analog signal. So if I have to express mathematically FSK, so basically your frequency is varying. So mathematically your FSK is expressed as something like this: V FSK T is equal to, now please note that VC cos 2 pi FC1 T for binary one. That means because the frequency is changing, so for one frequency, it will have a carrier frequency of F1, and for the other one, it will have a carrier frequency of F2 for binary 2. So that becomes my expression for the FSK. So just like we have in the case of ASK, something like this, that means 1 is any carrier frequency and 0, no carrier frequency. But here I have the frequency is changing for 1 and 0. So here, sorry, I have written 2 here. Binary is always 1 and 0. Okay. So in this case, it will be 0 here, and the frequency of the carrier will be different, FC2. So let's understand this thing in the waveform. So suppose I have a data, same data if I can take. So this is also we call the binary. Just a minute, please. Hello. Just a minute, please. Hello, good afternoon. Sir, I'm in campus. Right now, I have a lecture. Yesterday also, I'm now coming regularly. So, I wanted to discuss, but we right now have 12 to 1:30. So, after our EC meeting, after that, we can discuss. Yes, sir. Tomorrow we can discuss. So, next, sir, I also wanted to discuss. There are some issues. Maybe today we can discuss because it is urgent, otherwise tomorrow. Oh, fine. So 2:30, but right now. Okay. Sorry for that. So this is what we call the binary data sequence. Sorry. This is what we call the binary data sequence. So let's say 10111010. And similarly, if I go for this representation of PSK, I have the same representation what we have here. So let's mark like this. And Okay. So let's say I have some binary data sequence, some just like we had previously, or something else. Binary data sequence. Let's say I have 10111010. Okay, and my waveform will be something. It will look like this. So there is a 1 here, 0 here, 1 here, 0 here, 1 here, and 0 here. So that is my input digital data. Now, this is my carrier frequency. So I'll mark with the carrier frequency, let's say, carrier frequency, which is omega c, which is 2 pi fc. Okay. So I have certain frequency, let's say 2 pi fc. So my carrier frequency, let's say, is like this. So it is some high frequency carrier signal, which is I'm applying throughout. Now, how my PSK waveform will look? So FSK waveform, as I said, FSK waveform will look like this. So we'll have two frequencies generated, F1 and F2. F1 corresponding to 1 and F2 corresponding to 0. So let's say F1 is higher and F2 is lower frequency, let's say. So if it is higher, my waveform will be look like this. And now it is F2. So F2 will be like this. Again, I will get F1. So if you see, F1 is greater than the carrier frequency. And again, here I got 0 here. Again, I got F1 here. And again, I got 0 here. So here I have F1. Here I have got F2, F1, F1, F2, F1, and F2. So this is my FSK. The frequency shift keying looks like that. That here my frequency is changing. My frequency is changing, but my amplitude and the phase we are not considering right now. As I said, we have previously also we not discussed the phase modulation, but we'll discuss. They are linked to one another, as we have already seen in when we started the angular modulation. But here my frequency is changing. Amplitude remains the same, but in the previous case, the amplitude was changing. Either there is a amplitude or there is zero amplitude. So this is the difference between ASK and FSK. So basically, these are an extension of AM and FM, but only difference is the input data is in the form of a digital data. That means it is in the form of a binary data sequence, 10111010 or something like that. And based on that, you can have this one. So tomorrow's experiment, you will be doing like this. Nowadays we have the chips. So there you give the inputs to the desired pins, and you can see the FSK waveform, something like this. So you'll have the two frequencies. So one is greater than and other is smaller than the carrier frequency. And that's how this term is represented. So basically, here important thing is to be kept in mind, which is also there, which I will write here in the previous slide. FC1 and FC2 are offset frequencies, offset from the carrier frequencies, from the carrier frequency FC by equal, carrier frequency by equal and opposite values. That means suppose my FC is, let's say, 10 megahertz, FC1 could be 9 megahertz, so and FC2 could be 12 megahertz. So these are not the carrier frequencies. So these are the offset frequencies from the carrier. And that's why we represent sometimes as F1 and F2 also, but FC1 and FC2, it is one and the same thing, if you have understood the meaning. So these are the frequencies offset from the carrier by equal and opposite values. So one greater than, another smaller than. And obviously your FC1 will be greater than FC2 and so on. So this is about the FSK and ASK. Now we'll come back to the phase modulation, which was earlier. We are supposed to start. So this is, but sometimes we have to cope up with the experiments also. So that's why I brought it here, but it is an extension of AM and FM. So we'll talk about the phase modulation, which is we write as PM. So this is the topic. So it is again a angle modulation, just like your FM modulation. Now, if you recall, when we talk about the phase modulation, we said that something very interesting word I used, and this we are going to understand, which you also written something like that. In the phase modulation in PM, your frequency is varied indirectly. That means your frequency and phase, here also my frequency is changing, but it is varied indirectly. There we have seen in the case of FM, the frequency is varied directly, and that's why, and this PM is also called indirect FM. If you recall, we used this word when we started our analog modulation. So indirect FM. So it is some sort of a indirect FM. Again, if you recall, we talk about an angle modulation signal. So this is, I'm just recalling. Again, so this is, I am just recalling all those things what we started with the angle modulation lecture. Also, we have seen for angle modulation in general, which we started, your modulated carrier, which could be angle modulated carrier, is represented as, which you have seen. Modulated carrier means angle modulated, okay, as Vt is equal to Vc cos theta t, and where we have written as theta t is equal to omega ct plus phi t. Okay, this I am just recalling what we have done. And here my omega c is nothing, it is 2 pi fc. And if you recall here, which is my carrier frequency, okay, whatever you call, and phi t, we have talked about, it is called the instantaneous phase deviation. Whenever we use the word instantaneous, that means it is a function of the time. So this is the instantaneous phase deviation. Okay, so this we have discussed. And also if you recall, we have the modulated signal or the message signal as something same, which is my Vm cos omega m t, where my omega m, is 2 pi fm. Okay, so this is something we know. Now let's understand the various terms which are there just in the same line as we have done for the frequency modulation. So first, if you recall, we introduced a parameter which is what we call the instantaneous frequency or instantaneous radiant frequency in the case of FM wave, which is omega is equal to omega c plus d phi t by dt. Okay, so here we defined the first term, which is what we call the instantaneous. I am not able to go back to on my iPad, but yes, of the last lecture or the starting lecture of the angle modulation. But you can look into that instantaneous phase of the angle modulated wave, angle modulated, or here it is PM wave is defined as theta IT, okay, is equal to omega CT plus phi PT. Okay, so this is how we define. Just like if you recall, in the case of FM, we have what we call omega I is equal to omega C plus d phi t by dt, if you recall. Okay, which we have defined as instantaneous frequency, or because it is in radians, so radian frequency. Otherwise, if you go in FC or FI, so it is that one. So it is recalling in the case of FM. So here we have omega IT. Obviously, it is instantaneous. So whenever you use the word instantaneous, that means it is a function of the time. Okay. So here also I could write down like this. And this is what we got it last time. So here we defined the instantaneous phase of the angle modulated wave. That is the one parameter. And then you recall, we talk about the frequency deviation constant, which is KF. Here also we define the phase deviation constant. So again, I introduce one more parameter, which is on the same lines, instantaneous phase deviation of the carrier signal. So on the same lines, it is defined as phi. Again, P is for the phase modulation. Again, this is instantaneous. It is given as Kp into Vmt. Again, if you recall, for the AM1, I am putting also side by side rather than going to the back slide. You recall that we have d phi t by dt is equal to Kf Vmt. And again here my Vmt is nothing. It is the same message signal, where my Vmt is nothing. As I told you, it is the same message signal, which is Vm sine omega mt. Sine or cos, that doesn't matter, as long as it is a sinusoidal distance. And here Kp is what called a phase deviation constant. Phase deviation constant. Just like we talked about in this case, FM, your Kf is the frequency deviation constant. Okay. So here it is defined as the phase deviation constant. So this is a new parameter which we got it. Phase deviation constant. And then if you move further, now I could write my phase modulated signal also as, on the same lines, the PM wave can be, just look into the AM signal side by side. I am also trying to go in the same way here. So it could be written as Vpmt is equal to Vc cos omega Ct plus Kp Vmt. Just like I put it in the case of FM, your FM wave, which we represented as V FMT is equal to Vc cos omega Ct plus Kf VMT. Okay, so that's what we have recalled that one. Okay, so basically what you see here, it will change the phase of the original value. Let's do one example, just like we did in the last time. So we take one example now on the phase modulation. So we'll do one example. Suppose I have a signal VMT is equal to 10 to power 5 cos omega mt. No need to say it is my message. Again, I'm using the word modulating. So we have three signals. Message signal is a modulating signal. Then we have a carrier, which is an unmodulated carrier. And then we have finally the modulated wave. So three signals are always there: modulating, unmodulated, and then the final modulated wave, AM, FM, PM, whatever you call. So modulating signal is the message signal. Unmodulated is the carrier or the high frequency signal. Message signal is low frequency signal. And finally the modulated wave, which could be FM, AM, or PM. So in this case, let's take one example. So I have a message signal like this, and it is phase modulated. Okay, on an analog carrier signal. Last time we took an example immediately. It was frequency modulated. Okay, so now it is phase modulated. Yes, please. I'm having a lecture. Okay, fine. So it is the phase modulated of an analog carrier signal, which is a frequency of, let's say, 90 megahertz. Let's say. Okay. Now here, okay. Now here my deviation constant. Obviously, when you're talking about the deviation constant in the case of a phase modulator, so it is of the phase modulator. It is quite obvious. So that means it is a phase deviation constant. So it is a phase modulator is 5 radians per volt. That means Kp is given to me. Just now we talked about Kp here. If you recall this Kp has a unit of radians per volt. Okay, so it has got the units of radians per volt or per millivolt. These are the units for the Kp. Okay. Now here the Kp is given to be again, just look for the units here. There's the last time somebody asked a very interesting question, that the units are important here also. So it is defined as 5 radians per volt. And we have to find, yes please, 1 minute, let me finish this question and then I can find instantaneous frequency of the PM signal. Yes please, yes please. Yes please, go ahead with your question or doubt.
Yes sir, as you said that for FM the unit of Kf is equal to hertz per volt.
Yes, yes.
So how we can add omega t plus Kf into VMT, because hertz per volt into volt will give us hertz, and then we add with radian omega ct.
So I will just come to that. Again, you have asked the same question. So we just, when we answer this problem, you will understand. Just wait for that. That's why I'm taking this problem. Last time also you or somebody asked the same question, how the units are matching. We'll see to it, how the units are matching here. Let's talk about solve this problem and find out this one. Okay.
Okay.
So in this case, to understand, yes, your question is very valid, but let me see. So basically, if I have to find the instantaneous frequency, I will go to the next slide. I think that's really better. So go to the slide. So I have to find the instantaneous frequency of the PM signals. Slightly it is, because we have seen that it is not straightforward. It is, say, indirect FM PM signal. is given by f of PMT. Okay. If you recall, it is given as the phase, my frequency of the carrier, and then it is changed to the phase part. So let's understand how we solve this thing. If you recall, it is given as FC, because now I'm dealing with the frequency 1 by 2 pi d by dt of phi t. Okay. Okay. Just again, I'm saying, recall what we have seen here, or just now also, and previously also, in the terms of omega I, it is given as omega C plus d phi t by dt. But now we are dealing with the frequency, so everything I converted into a 2 pi. So this is 2 pi f, this is 2 pi fc, and then it becomes 1 by 2 pi, and so on. So I could write down this expression as, okay, as fc plus 1 by 2 pi d by dt of, now phi t is nothing, as we have seen earlier. How we define phi t is kp vmt. Okay. See, if you see here, so what is kp vmt? Kp has got the units of radians per volt, and vmt is a complete signal. Okay, complete master signal, which has frequency, phase, everything here. So phi t is nothing. It is kp into vmt. It is a complete signal. Again, I will write down here, since phi t is equal to kp vmt for a phase modulated wave. Okay. So nothing great we have done. So I could also write down this as fc plus kp over 2 pi. This is a constant, so I've taken it out. Again, I'm just showing it to you. This kp we have written as phi t is written as kp vmt. So same thing I am putting here. Okay. And we'll see also, and which will answer your query. Now I put the kp is a constant, so I took it out, and d by dt of vmt. And vmt is given as, so I will write as d by dt of vmt, and vmt is given to be, just now we have seen 10 to power 5 cos omega mt. Okay, nothing great. Or I could write down this as each and every step done for you. 10 to power 5 is also constant, into kp is constant, by 2 pi, again it will be out, d by dt of cos omega n t. So it can gives you fc plus 10 to power 5 kp over 2 pi, and maximum value if I have to find, because it says find the maximum instantaneous frequency, because the frequency is changing here. Phase modulation is an indirect FM. That means the frequency is changing. So if you see, I am writing here, find the maximum. So I will just write it very clearly. And the question is find the maximum instantaneous frequency of FM signal, of PM signal. Deviation constant, oh, this also got rubbed, of phase, I think it was modulator. Okay. So basically I have to find the maximum, because frequency and phase are related to one another, as we have seen from this expression, that omega is equal to omega c plus d phi by dt. That means if I'm changing the phase, my frequency is also changing. So, but my problem is find the maximum of the instantaneous frequency. So to find the maximum of the FM frequency, maximum of FM t is given as d by dt of cos omega mt, maximum of that. Okay, so I have to go for that one. So I could write down this as fc plus 10 to power 5 kp by 2 pi, and maximum value of cos is 1. So this becomes my maximum value. So I could write down as maximum, because my frequency is also changing. It is an indirect FM. PMT is, and why it is indirect? As I said, it is a, as you see here, it is omega c plus d phi t by dt. So my phase is changing, in the phase modulation, so my frequency is also changing. So it is an indirect FM also. And then it is given as FC plus 10 to power 5 kp by 2 pi. Now you have to just put the values, and what we are given, FC is already given to be 90 megahertz. Again, everything you convert into hertz. That is very important, because in one problem you will be dealing with the kilohertz for a message signal, megahertz for a carrier signal, and so on. So this becomes, so every time you have to put the unit in hertz to avoid any confusion, and kp is given to be 5 radians per volt. So in this case, it turns out to be 5. If I have to convert into the frequency only here, I will convert into 5 radians per volt by 2 pi. Okay, because I am converting everything from a angular to the normal frequency. So radians to the normal frequency. Okay. So in this case, my maximum value of FPMT is given as 90 into 10 to the power 6. I am putting the units to answer your query, plus 10 to the power 5 volt into 5 radians per volt and divided by 2 pi. Okay, so volt and volt will cancel, and radian by 2 pi will become hertz only. So it becomes something like this: 90 into 10 to the power 6 hertz and plus 0.08 into 10 to the power 6 hertz. So that becomes 90.08 megahertz. Now from this pollution, so this is the maximum frequency. Now with this problem also, hopefully I have answered your query why the units are not matching. Now here if you see, this is the unit of hertz, this is the unit of hertz, this is also volts into radians per volt. So that becomes radians, and radians by 2 pi is nothing. 180 degrees 2 pi radians, so 360 degree 2 pi radians. So it is basically radians by 2 pi is your normal frequency. So that's why I think the units are understood here. Okay, is that what the query? So in my PM wave, the frequency, which I think was your doubt, it is the unit of this thing. Though we are dealing with the radians per volt, and on the left hand side it is hertz. So this also turns to be hertz. So this becomes hertz. So important thing is to be kept in mind this, which I think was your doubt. And this is also hertz. This is also hertz, and this is also in hertz. So I think this was your doubt.
Hello, sir.
Yes, please.
Sir, can you go previous slide?
Yes, please.
So here we have to deviate cos omega t, so it will be sin omega t into omega t.
So it will be like omega into sin omega t, the maximum value could be 1.
We have not included omega m. Sorry.
No, because your omega m will not be there. Omega m is the complete function is there, but maximum value of that will be for that particular frequency, it will be that only 1. Omega is nothing, omega m is nothing, it is 2 pi fm. Okay, I will clear it out. Let's do one more example. Just to clear everything. But before doing that, I have to introduce certain parameter also. Now, if you recall, in the case of when we talk about the FM, again, I am dealing with side by side also, exactly the same way what we have dealt in the this thing, modulation for the FM. So same thing I'm doing in green also, side by side for the phase modulation. So yes, that thing will be clear again. So let's talk about a new parameter, which is, I put it as modulation index. Like we have the frequency modulation index, MF, also when we talked about this thing. So here also we talk about the modulation index. So first we talk about we talked about the frequency deviation there, we'll talk about the phase deviation and the modulation index both. So we'll discuss phase deviation and modulation index. Obviously for a PM wave, phase modulated wave. Okay, phase modulation is quite obvious. Okay, so here, just like if you call the peak frequency deviation, okay, which we defined as delta is equal to MF into FM, or delta F is equal to KF into VM. So here also we defined the phase deviation as deviation is very important to note that proportional to instantaneous amplitude. Here, if you keep the units also while solving the problem, you can never go wrong, as I am doing that. Because here it is a bit confusing. Some parameter has got some unit and the parameter has got some unit. So just to come at the right answer, convert everything into hertz, try to convert everything into omega into 2 pi f, or f equal to omega by 2 pi and so on, so that you get the answer in the same thing. That's very important. So this is the amplitude of the message signal. Okay. That is your phi p is equal to kp into Vm. Okay. Now this phi p is equal to kp into Vm. Just like in the case of FM, I put it here, recall again for the FM. So simultaneously I'm putting the same thing here. There we talked about delta F is equal to kf into Vm. Okay, there we talked about this one. Okay, so here it is kp into Vm, where my Vm is nothing, it is the same. Sorry. Is the instantaneous amplitude. So Vmt of modulating signal in volts, and Kp is the phase modulator sensitivity. Okay. Just like if you recall in this one, here my Kf is the, which we defined as the frequency sensitivity of frequency modulator. So this is nothing, it is the phase modulator sensitivity in the same way as we have in the case of the frequency modulation. And the unit of phase deviation, its unit will be of phi p is radians. Okay. So Kp has the phase modulation sensitivity, and which is in terms of radians per volt. Okay. And unit of phi p is radians. Radians per volt into volts. So it becomes radians. Just like in the case of delta F, it was expressed in terms of hertz per volt. Please note that there it was expressed in terms of the hertz per volt, but here it is in terms of the radians only. Okay, not per volt. Okay, so that is the important thing to keep in mind. So basically, what we see, your phase deviation phi p is directly proportional to the instantaneous amplitude of the message signal, or directly I would also say linearly, because this is a linear relation. Okay, proportional to the modulation index. So this is we define the phase modulator sensitivity. So also I could write down this as Kp is equal to phi p over Vm, which is the phase modulator sensitivity, and that is expressed in terms of in radians per volt. Sensitivity means how sensitive its value is with respect to one parameter. So it is always with respect to certain parameter. So how much phase is changing? Phase sensitivity means how much phase is changing and why, how the phase is changing with the modulating signal amplitude. As I said, we always vary in accordance with the amplitude of the message signal, whether it is AM, FM, PM. So it is expressed in terms of radians per volt, as in the case of the frequency deviation constant. Okay. There we have also another term, what we call the carrier swing, which is the peak to peak frequency deviation or 2 delta. Here we don't have that concept here. So here this Kp is given by this one. So please note that it is slightly different. And now we talk about the important thing, which is the modulation index. So here we talk about the phase modulation index. On the same lines as we talked about MP. Just like we talked about the frequency modulation index, so I'm putting it side by side for also recall for FM. What we have the frequency modulation index, and that was we denoted as MF. Okay, so here we go for FM. So how to define this? Now in this case of phase modulation index, it is expressed in terms of radiation and is defined as the peak phase deviation. So basically, I will write down here and then explain. Your MP is given as Kp into capital VM. Just like in the case of frequency modulation, if you recall, what we have something MF is equal to delta over FM, okay, or KF VM over FM, okay. Because in this case, which we have defined as delta is equal to KF into VM, okay. So this becomes Kp into VM. So this is expressed in terms of the phase modulation index. So phase modulation index, sorry, I use the same color. It is expressed in terms of radians. Why? Because it is radians per volt into volt. So this will cancel. So this becomes it is expressed in terms of the radians. And just like we have in the case of the frequency modulation index, and the frequency modulation index didn't have any units, okay, didn't have any units as we have seen in the previous case. So this is the what we call the phase modulation index. Let's do certain example as we have done in the previous FM also for the phase modulation index. So I take one example here. Okay. Suppose I have a phase modulator, let's say, has sensitivity, which we have just discussed, of, so I say Kp is equal to 2 radians per volt. Now I have to compute the RMS voltage of modulating signal, which will cause phase modulation index of, let's say, phase modulation index means MP of pi by 3 radians. Please note that the index is, phase modulation index is given in terms of the what we call the radians. Okay. Unlike the frequency modulation of this thing. So this is a simple problem. But yes, how to solve this? Let's see whatever we know. Now, MP is given as Kp into Vn. which we have just now seen. That's how we have to calculate. Or we have to find the RMS voltage, which means I have to find out Vm, which is MP over Kp. But here, my Vm is peak modulating voltage, not the RMS. Okay. And peak is nothing. You can change RMS value to the peak value by root 2. Okay. So in this case, my Vm turns out to be pi by 3. So I'll put the units. So that's how we should work. Radians divided by 2 radians per volt. So it turns out to be pi by 6 volt. Always put the unit, so you'll never go wrong. So it becomes by something like 5.524 volt. But this is the peak voltage. This is the peak voltage. And therefore, RMS voltage is nothing. It is the peak voltage by root 2. That's, we should know always, root mean square. I think that's also I've told you. So this is what we call the root mean square. Okay. Or sometimes it is called the effective voltage or something like that, but root mean square voltage is very common. So in this case, it turns out to be 0.524 by root 2. And that's turned out to be 0.37 volt. Because in the lab, sometimes, most of the times we measure the RMS voltage also. So that is another example. So this was the example based on the phase modulation index, which we just calculated. Let's talk about the maximum phase deviation also. How much maximum, just like we had the maximum frequency deviation. So let me see if I could have a maximum phase deviation also, if some problem I could find out. Okay. Okay, let's take one more example to clear everything. So let's say I have a angle modulated carrier because we are dealing with the phase modulation. So obviously it means the phase. V 20 cos 100 into 10 to the power 6 pi t. Important thing to be kept in mind, always look for the units. If you are not sure, then put it in the, so pi already we have introduced here. So it is 2 into 10 to the power 3. Let's say this is the one, and this is using phase modulation technique. And I have to find the carrier signal frequency. So it is quite obvious how to go for that. If I have to find this one, your VCT is equal to, what we have learned is VC cos omega CT plus phi t. That's something which we know. So if I compare these two, it means your omega c is nothing. It is 2 pi fc. It is nothing. It is 100 into 10 to the power 6 pi. Okay. Omega ct is given. So this is nothing. It is your omega ct, which is omega c, which is 2 pi fc. So omega c is, if I compare that from this expression, your omega c is, sorry, I get 100 into 10 to the power 6 pi, comparing the two equations. Okay. If I see from this, this is this one and this is this one, which means your 2 pi fc is equal to 2 pi 50 into 10 to the power 6, and which means my fc turns out to be 50 into 10 to the power 6 hertz or 50 megahertz. Okay, so my carrier signal frequency turns out to be 50 megahertz. Okay, and if I have to express my phase modulated signal, is VPMT. Suppose I have to express that VC cos omega CT plus MP sin omega MT. Okay. Now, if you see here, let's say I change the question to this one. Find number 1 and number 2. Also, we find the maximum phase deviation. So this is the part 1 and this is the part 2 if I'm doing. So if I compare these two, comparing, what we get here is your VCT is equal to 20 cos 100 into 10 to the power 6. Sorry, that is already given there. I need not write. So if I comparing that equation, what I missed here, this is VPMT, the phase modulation. So if I comparing these two, what we see here, MP and MP is here. So we get MP and sin omega MT. So this becomes my sin omega MT. So MP turns out to be 5. MP turns out to be 5 radians. Okay, so in this case, my MP turns out to be 5 radians. So this is, oh sorry, I put it here. Find phase modulation index. Okay, so if I got this thing, so basically you will get the same thing. Now let's understand the relation between. So what we have understood, this is all about the FM, PM. Now in one simple slide, which is the last one, I will try to explain relationship between FM and PM. We have seen the FM waveform, if you recall in one of the lectures, how my FM waveform looks. That means maximum negative deviation, maximum positive deviation, maximum negative zero crossing, zero slope, and accordingly we have drawn the FM waveform. So how to draw the PM waveform, and what is the exact relation between FM and PM, and what is the disadvantage of PM, and then we compare the FM and PM in one simple table form in my next lecture, which will be the last lecture of angle modulation. Once we cover that, we'll talk about the noise, which is the last part and not a very detailed part. So that will cover in the lecture, in the next lecture itself. And that will be the portion of my mid-sem exam, which we have sent the mail, both myself and Deepak Godgaonkar. We discussed together and one of us sent the mail. Normally Professor Deepak Godgaonkar is senior to me. So I gave him the opportunity, but we go through that and rewrite all those things. So regarding the exam and some queries and other things, we'll discuss in the last lecture before the exam, that is on 8th of May. So 1st of March, that is Tuesday, the next lecture will not be there because it is an institute holiday because of Shivratri. But yes, don't worry that all the lectures are already taken into account. So we'll have a lecture on Tuesday or Wednesday, 2nd of March. There we'll talk about the remaining part of PM and the noise part. And then we have the next lecture on Tuesday, 14, which will be like it is not mandatory. It is just will review about the exam and other thing. We'll discuss also about the exam in the next lecture also, if possible. Otherwise, on 8th, before the exam, we'll talk about the examination pattern and everything, which anyway, we have sent it to you also in detail. So 2 more lectures, one normal lecture, another is a type of revision and understanding of the examination pattern, which we already sent. So then we'll finish this analog communication part, and after the exam, we'll talk about the new part, which is the transmission line theory, and that we'll be able to cover in the remaining 11 lectures. So that's all about today. Any doubt, any query? Nothing in the chat box. Somebody was asking something. Now, hopefully his doubt must be cleared. Okay, so best thing is to avoid any doubts. When you solve the problem, important thing, convert everything into hertz, because in the same signal, as you see here, I may be dealing with the FC also, carrier frequency, which is normally a high frequency, typically megahertz. And also I'll be dealing with a message frequency, which is typically in kilohertz, low frequency. So we are dealing with the 2 different frequencies in the same problem. So convert everything into hertz. Also go on putting the units as we have done in various examples. The moment here I do these examples, like when I'm calculating the VM, I'm also putting the units also side by side. That MP is in radians and KP is in radians per volt. So I got volt, and the left hand side is also volt. So you will never go wrong. In the previous example also, if we see, always look for the units also. So then you understand, because otherwise it's a bit confusing, because some parameter is having units of volt, another is radians per volt, some maybe radians per hertz or volts per hertz per volt or something like that. But once you have these slides, that's why I put it in the green color also side by side, so that at one place you are also knowing what we have talked in the frequency modulation, the same parameter, just like we have done it here. So with this, I'll stop it here. No more question. Otherwise, we can discuss and clarify in the last lecture also all these doubts and so on. So one more lecture on this analog communication part, and then a revision type of the lecture on 8th, and after that exams and the holy break, semester break, which will be, I think, from 22nd of March, Tuesday, we'll have our the transmission line theory until the end of April. And the first week of May, the exams are there. So that's all. I think there's no query. So I stop it here. I have already posted all. Plus. Yes, please. Yes, please.
Sir, can you please go to the previous slides?
This
Example
one?
number 1.
Example number 1. Okay, I could not recall. This one?
No, sir.
Huh?
No, not this one.
Oh, before that. Okay, let me see.
Yes, sir, this one.
Mm-hmm.
So here you took the derivative to be 1, like maximum value to be 1. But
But
the
omega,
argument...
I got it. I got your point. I also realized when you talked about things. Yes, please correct it. It will not be 1. It will be omega. Okay. Because cos d by dt of cos of omega mt. Okay. So
Sir, also there would be a -1 sign. So the maximum value could be FC only. Because we would have to reject the second part.
Yes. And the minus part normally in our communication system is basically the change of phase. Okay, as I told you. Okay. Fine. What you're saying? Please repeat what you're saying.
So, sir, like we would have to take derivative first, right? Cos.
Yes.
So we'll get minus omega m into sine omega mt.
Yes.
And now if you want to make it maximum, you would have to make this second term minimum.
Yes, second term minimum.
Yeah. So
because
so
of
we would have to take omega m equal to 0.
Okay, just give me time. I will correct it. I think you are right. Because When you're taking that one, it is omega m sine omega mt. Okay, am I right? This you need to say?
Yes.
Yes, I will do that. I will correct that. I will correct that. Right now you can forget this example. I will correct it. Okay. So
Okay.
right now you forget this example. Okay. Yes, I realized your mistake. Because here also I am solving on my own here. So yes, I realized that mistake. So what I suggest to you, I will write it here. One important thing so that you will not miss it. Let's ignore this problem for the time being. Okay. Ignore it. We'll come back with the correct answer. Okay. Okay. Fine. And I'll come back to you with the correct answer. Okay. Yes. Anything else? Any other query? It was a good, yes, good. Fine. So